So we were talking about the multi-layer perceptron, right? So fine now?
Yeah.
So in the case of the multi-layer perceptron, as I said, we if you see in this case, since we are going into more of the deeper, but we do face problem when we are going to talk about the image data. Like right now, we have discussed or we have seen data which are real numbers or maybe the discrete numbers. We were talking about the numbers. But since we are using the EV or EV systems, definitely we are going to have visions or the cameras which are going to take the pictures, right? So how we are going to hold or we are going to handle such data, right? So I'm not saying the fully connected neural network is not going to work. It will work, but the problem is at the end we are looking only for the accuracy. We want a good system, right? Or with a good model with a stable as well as a very high accurate, which should be accurate as well as a stable too, right? So you see, the feed forward is going to work very well, either it is for the regression or is it for the classification. But when it comes to the image data, there are so many problems which it faces. The the biggest problem is, let's just consider a very small example of an image, which is 25 cross 25, right? One image is 25 cross 25, so exactly it is going to be 625 values, right? 625 pixel values are going to be there, right? So now one image, which is going to be considered as a data, is going to have 625 number of elements, right? So 625 element per image. One image, now how many number of input neurons I should be having? 625. Right? Because 625 elements are there for one image, which is one data, right? So 625 number of input neurons will be there. Then there is going to be hidden layer. So let's assume that I am having only one hidden layer, right? Which is having, let's say, 100 number of the neurons, right? Then I am having one output layer, neuron, stating whether this image belongs to the, let's say, cat or dog. I want to classify a particular image whether it belongs to cat or dog, right? So one output will be there, just saying whether it belongs to class 0 or it belongs to class 2, right? But you see how many number of weight connections we are going to have. In the previous case, when we were talking about like this, the number of the connections are going to be smaller when we are having real numbers. Why? Because let's take 5 parameters, or let's say 20 number of the columns are there. So 20 columns means 20 number of the input neurons will be there. But when I am taking one image, which is a 25 cross 25, I need to first convert into the I need to do the flattening. Flattening is just converting to one single row or one single column. So it is going to be 625 elements. Now 625 element is the number of the neurons. So how many number of the connections will be there? 625 cross 100 number of the weight connections will be there in between input and hidden layer. From hidden to input, output layer is also going to be 100 cos 1 number of the connection. So total number of connection here it is going to be very high compared to when we are talking about the real numbers or let's say time series data, right? So you see, in this case, the number of the weight connections has been increased. The complexity of the architecture is now increased. So it may take too much time. The time complexity is going to be higher when I am going to predict something or classify something, right? So this is the one biggest issue. That the time complexity is going to be too high. Another thing is, since the image itself is having very, you can say the information it carries in the pixel, it is very, very important and they are very large in the numbers, like the range is from 0 to 255, right? So when we are even doing the normalization and all, when we are predicting, when we are classifying, let's say, in that case we don't get good results compared to CNN, which is the next architecture that I'm going to talk, right? So it says that since in the ANN or simple multi-layer perceptron, we are having so much complexity in the terms of the weights or in the terms of the time, even the space is also very high because we are going to have now several number of the neurons. So I need to store that much of data also, right? So it says that we have another version or another improvement over the multi-layer perceptron, which is CNN, which works very well for the image data. So the next one architecture is the convolution neural network, which is the improvement of the neural MLP only for the image data. It's not that it will only work for the image data, it will work for the real numbers too. But mostly it is for the image, right? So in the convolution neural network, what happens that we are going to now have an input which is going to be image like this. Now in the convolution neural network, we have two layers. Basically, first one is convolution layer, next one is the pooling layer, right? So in this diagram, we have represented both of them together. So the image data comes up. On that, we apply the convolution, and on the same we apply the pooling. Whatever the result comes up, then it is passed to the fully connected layer. So it's the improvement of the fully connected layer. So what we are doing is it's same as the previous one. Fully connected layer is a multi-layer perceptron only. It's nothing different. But what we have done is, before we are passing the whole image to this fully connected layer, what we did is we have gone through this two layer, one is convolution, the pooling layer, to minimize the image and to change the feature into the smaller feature. For example, that my 225 cross 25 image can now be reduced with the smaller size of maybe 4 cross 4. That can happen when I apply the convolution and the pooling together. So now see, let's say if I have now 4 cross 4, after applying these two layers, I got 4 cross 4. So if I do the flattening now, if I create one single row or column, how many number of nodes I will be having? 16 nodes, right? So instead of having now 625 number of input neurons, now I am going to have only 16. So what we did is, in these two layers, we are either reducing the dimension of the image, or along with that we are changing the feature to the smaller size. Not a smaller size, actually we are sharing the weight rather than too much in the detail. Actually I cannot discuss in any depth. But in these two layers, what we do is, we decrease the size, we minimize or downsample the size. Along with that, we ensure that whatever the feature is there in the original image, the same feature remains there. Right? That's what we do. So now the same image of 25 cross 25 has been converted to 4 cross 4. Now this 4 cross 4 is equivalent to 16 number of elements in the input layer. Now you can decide how many number of the hidden layers or hidden neurons you want. Based on that, this is the output layer and the output has been generated. Right? So in these two layers, what happens? I will give a very small, just what happens in the convolution layer. So just consider that I am having an image which is of, let's say, 6 cross 6. Let's assume this is 6 cross 6 image, right? 6 cross 6 image is there. So what happens is, in the convolution it says that whatever the layer is there, I need one simple filter, one kernel function is used, or sometimes we call it as a filter also. So the size of the filter is there. Filter is defined, so it is mostly even, the size of the filter is mostly in the terms of the odd number. So let's assume it is a 3 cross 3 filter. And I am assuming my image data which I have taken, it is a binary number. It is either 1, 0, binary number, or it could be colored image also, it is 0 to 50. Assuming it is a binary number. What happens, this filter, which is a 3 cross 3 size, so let's assume this 3 cross 3 filter, is also some binary number. Right? Now what happens, this filter is placed on this whole image one by one on the basis of the cell. So first this filter will be placed on the first 3 cross 3 cell. So based on that, one output will be generated. So how the output is generated, it says that whatever the value is in this filter for the first cell, it will be multiplied by the element in the first cell of this image, sum them up, then again 0, but I'll calculate the value here. Okay? So I'm placing this printer on this image in the 3 cross 3, first 3 cross 3. So what will be the output? 0 into 1. 0 into 0. So I'll write in very short. So assuming whatever the elements were there, right? So what happens if whatever is the element at the first place and whatever is there, this is the first 3 cells, right? So I'm calling this x1, x2, x3, x4, x5, x6, x7, x8, and x9. And this is 1, 2, 3, 4, 5, 6, 7, 8, 9 cells, right? So the first 3 cells, this will be multiplied with this will be multiplied with this will be multiplied with this. The second will be multiplied with this, same, right? They will be all multiplied as a dot product, then sum them up, right? So whatever the value comes up, that will be placed in the new image, and the size of the image will be now reduced to 4 cross 4. 4 cross 4.
In the middle. Use
okay.
the middle space.
So this is going to be a 4 cross 4. Actually how? Because if you see the first 3 cross 3 I have used it, next what will happen is strike will happen. It says that now move this filter to the next 3 cross 3. So now again the first column with the 3 will be, it will be moved to the next line, and now I will take from 2 to 4, and from here 1, 2, 3 cell will be taken. So I'm again going to put this filter on this whole image with the next 3 cross 3 cells. I'm moving the filter on the image one by one. It's moving into the columns, right? But I will show that the filter should be on the image itself. It should not happen that now last two columns are there. So I cannot place my filter in such a way that the 2 columns are on the image and the other columns not on the image, right? It should not happen. So because of that, what will happen? 2 of the column will never be filled. So if it is 6 cross 6, so the output image which will be generated will be 4 cross 4 because the next 2 cells are not being used. Okay? So this is how we calculate the output, and this output is now generated after the convolution. So this whole process is convolution. By taking the original image, having a filter, then applying the filter on the original image and generating the result which is a 4 cross 4. Now this convolution output which we have got, on that we apply some pooling. Pooling is simple and downsampling. What it says is, whatever is the size of the image after we have received from the convolution, make it to half. Most of the time we go with half. So it says that if it is 4 cross 4, now it will be converted to 2 cross 2. So there are different type of pooling. Pooling is simple downsampling. So it simply says that whatever we have got, like 4 cross 4, it will be converted to 4. So let's just take a very small example. If it is, let's say 4 to 8, 6. Now if I do, so it has to be 4, 5, 7, right? So now this is a 4 cross 4. When we do the downsampling, or you say the pooling is applied, what it says is there are different types of the pooling. One approach is the max pooling, right? So I'm telling you that only. The max pooling, it says that if I'm applying the max pooling to 2 cross 2, so it says that whatever the whole image is there, divide into the block of 2 cross 2. So just we have to create 2 cross 2 block. So this is the first 2 cross 2 block, this is the second 2 cross 2 block, this is the third 2 cross 2 block, and this is the fourth. So we are having 4 2 cross 2 block. In each block, whichever is the max, since I'm using the max pooling, so whichever is the max will be considered. So in the first case, 8 is the maximum. So from the first block I got 8, from the second block 6 is the maximum, in this one 9 is the maximum, 3 is the maximum. So now I say this was the original image that, let's assume that we got it from the convolution. From the convolution, after that we have applied pooling. Right? So we have applied the pooling and we got 2 cross 2. Right? So now we have decreased size. Initially we had 6 cross 6. Now we got 2 cross 2. Now 2 cross 2, if I am passing through the fully connected layer, now the time complexity is also going to be reduced because it will take less time to generate the result. Along with that, the space complexity is also going to be reduced. Right? Now, it doesn't mean that whatever the data we are having, it has lost the feature. It is still having the feature, but with the lesser, a little bit of lesser information, but it still has the information. Okay. Now after that, we are generating the output. So in most of the cases, we apply the CNN for the classification. Most of the cases, but we can do it for the regression too. So you can search on the papers which we will get for both of them, classification as well as the regression. So this is just a pictorial representation of what are the steps that we have. I'll explain one by one. So this is these are the codes which you can find it in the Python in the Python code, which is available in the tensor and the keras, both it is available. So what we are doing is just assume that we are having a one single input which is coming. Now we have assumed that we are going through two layers, convolution and coding. In the CNN, it is not fixed that how many convolution layer you want to use or how many times you want to use the coding. You can apply two convolution, two coding. You can apply one convolution, two coding. That is your choice. There is no fixed rule that how many times you want to apply this particular layer, right? But the basic one says that we go with the one convolution and one coding, right? Just now I have explained how the max pooling works, right? So I'm going through the same. So I'm assuming that we are, if you are writing the code in the Python, right? So this code is already there as a package. It's available. So what we are doing is we are writing the code as model2.add. So what we are doing is model2 is a defined function which is already there. So in that we are adding the convolution layer. We are saying adding the convolution layer with the image, which is with the image size 28 cross 28. So this code is directly available, but I am explaining what these terms would be in the terms of the function. So convolution layer is being added. Now we have a convolution 3D2, right? We are using 2D here. So I am saying that I want to have 25 filters, which is of 3 cross 3 size. In the previous example, I took a one filter, right, of 3 cross 3. Here it is a 3 cross 3, but how many filters we are using? 25 filters. Along with that, we are taking the input image, and the size of the image we are now saying is 28 cross 28, right? And there is the next term which is 1. So when we have the image data, it can be the RGB image or it can be a simple grayscale image. So if it is 1, it means it is a grayscale image. If it is 3, it means it is a RGB. So what we are doing is we are having the 3 cross 3 filter, which is 25 in the numbers, right? And the size of the input image is 28 cross 28. Or you can say 28 cross 28 pixels, right? Next, after that, we will apply the convolution. So when the convolution is applied, whatever the size of the image is there, it will be reduced by 2, right? That's what the general approach is. But there is another term which is called as a padding. Padding says that I don't want my image to be reduced to the smaller size. I want it to be same. Right? If it is 6 cross 6, it should be made as a 6 cross 6. But it is not possible unless I add some more columns to the input image. So I can add 2 more columns with the value 0, 0, 0, 2, 2 or any numbers which you want. Based on that, my original image was 6. I added 2 more columns, it became 8. When I apply the convolution, again I will get 6 cross 6. Fine? So that's what we are doing, right? Padding can be done, but those functions are not mentioned here. So once the convolution is applied, we will go to the pooling, right? So in the pooling also it is predefined function. So we can add max function size 2, 2. You can write 4 cross 4, 3 cross 3, 3, that is your choice. Right? So we are starting with the convolution function with adding an image with the 25 number of the filters of size 3 cross 3. So what is happening? One image is 28 cross 28. Now if I apply 25 filters, how many results will be generated? 25 results will be generated. Because each filter is different. One filter is generating one output image. 25 filters applied, I'll have 25 output images. So 25 output images, but with a reduced 2 size because we haven't done any padding. Okay. Now after that, we are adding the pooling. So 2 cross 2 pooling. So the size of one image will be changed to half. So now it should become 13 cross 13, right? So each image is now 13 cross 13. The number of the images which we are having is 25. Again, if I am applying, we can stop at this point and we can directly pass to the fully connected layer. But I am again going with the convolution layer. So again, if I apply the convolution, I have to again define the number of the filters. So let's say I am again taking 50 number of the filters, 3 cross 3 size, right? Now again, what will happen? If I apply the convolution, this size will be reduced by 2. So this is 11 cross 11. And on each image, we have applied 50 filters. So 50 images will be generated. Now on those 50 images which we have this will be reduced to half. So now it will become 5 plus 5. After that, whatever we have now. So these are nothing, they are just telling that how many parameters we are having. Since we have three cross 3 filters, so the number of parameters in each filter is 9 inputs. Here again we have applied 3 cross 3 filter, but we already have 25 over here. That's why 9 into 25, that is right? So the total number of the parameters for each filter. Now later on when we have this, same thing, we are going to do the flattening. How many number of images we are having? 50. From this one, 50 into 25. Actually, no, there are 50 into 25 number of images. But for now, one image is going to go, which will be having 5 cross 5 along with 50. So I need to add a flattening layer. Flattening layer, I'm going to convert into the one single row or column. So in the same model, I'm adding flattening. After that, what is the size now? 1250 number of nodes are there. Now, fully connected layer is the now, when we are adding the fully connected layer in the TensorFlow itself, it is mentioned in the same layer. What we are doing is, you see, the same model we are adding everything. In the same model we added convolution, then pooling, again convolution, then pooling. Now we have added flattening. Now a single column has been created. But after creating a single column, the next task is to pass into the fully connected layer. Right? So what we are doing is, first add the dense layer. Means we are creating one layer which is having the number of dimensions. The number of the neurons is 100. So we have created one layer with the 100 number of neurons. After that, we need to apply the activation function. Like in the previous example, I said we can have the sine function or the sigmoid function. But in the most of the cases, when we have image, we go with the ReLU function. Rectified linear unit activation function. Whatever the output comes from this layer, it will be a ReLU activation function will be applied. After that, we are saying, now I don't want to add any more layer. I'm just adding the last layer, which is the output layer. How I got to know this is the output layer? Because I took an example here that I want the particular image to be classified into 10 categories, whether it belongs to either of any 10 categories or not. So I had 10 output neurons, so that is my last. And from in that output neuron, output layer also, I'm applying the activation function, which is softmax. Softmax is same as a sigmoid activation function, right? So we have added one hidden layer here, which is having 100 number of neurons. Writing twice, it will become 2 hidden layers. If you are writing thrice, 3 hidden layers. And the last layer, dense layer, says that this is the output layer, right? So based on that, if you see the whole architecture that what we have done is, we started with one single layer. Later on, we are classifying. Similarly, in your problem, you have to find it out where you are going to classify, for which particular thing you want to classify. Then you can use the CNN. Okay, so it's an engine. But this CNN, it was used 20 years back. Right? This was originally the simplest one. Later on, there are other versions of the CNN which has come up, like faster CNN, RCNN. Right? These are the newer versions, and the latest one is YOLO that most of them are using now. Even for that later also there are different versions which has come up. Recently it is YOLO 8 and YOLO 9 which is present. Now maybe that can be also used. Okay. Now, so this is all about the CNN. And see there are different architecture of the CNN. That this is just the timeline to show. Started with the VNet. Right, the basic was CNN. After that there was some more modification which was made. Then VNet, VGGNet, GoogleNet, ResNet and MobileNet. This was till 2017. But in the last 6-7 years also, there are so many other modifications which have came under the CNN. So in all these architecture, the work change which is happening, how many number of convolution layer are added, how many number of pooling layer are added, what is the architecture of joining them. For even if you see in the VGGNet, we have VGG 15 and VGG 15 and VGG 19, 17 and 19. So there are two types of the VGG. So it says that only the difference is the number of the layers which we have used. Right? The number of convolution layer or the number of the pooling layer which we have. And in the GoogleNet we have a new concept was proposed which is called as the inception model. Right? So they are basically started from the CNN, but there are small modification has been made in all those CNN, and they have named it for the different. They have even all these models, they have been tested on the platform which is there is one actually failure. Every year there is one challenge which occurs. There are millions, trillions of the image data are uploaded there, and different agencies in the companies they involved in that, proposing their different models, saying that my model is working well. So later on there is a winner. So for one of them, AICTE and PGG network, the winner for that particular challenge. Now this is another one, recurring neural network. It is not good for image data. It works very well for the time series data. You see, in the case of the artificial neural network, what happens? The data it is considering is stable. Like it doesn't matter whether it is a real time data or it's a very long data. It is considering as a time series, but it is not considering the dependency between the data. Right? It is only taking that yes, the data is there, which is a simple non-linear data, but it is not considering anything as a temporal dependency between the data. So in order to do that, we have recurrent neural network. It says that whatever the output is coming, the same output can be considered as an input for the next, in the latent stage. For example, in one of my research, if I say that whatever is the electricity being used this Monday, there is a probability that same electricity will be used, same amount of electricity will be used on the next Monday also, right? So today's consumption of electricity is dependent on the next Monday, right? Even whatever the consumption is happening on the weekdays, the same amount of electricity is probability is that the same amount of electricity consumption is going to happen whole weekday in the next week, or maybe after a month also. But yes, if the season changes, the amount will also change, right? So there is always a dependency. So if you see, if I am using a simple ANN, right, it is not going to work very well if I am going to combine it with some other model which can learn the temporal dependency, right? So RNN is one of them. So this is the basic architecture of the RNN, right? So I'm not going to go into very detail, but I can explain what it is here. So it is very similar to your previous neural network. We have the input layer, we have the middle layer, we have the output layer. But the one thing which occurs in the recurring neural network is whatever the output is coming, that should come as a feedback again into the network and generate the output. So whatever the output was generating in the middle layer, the same was passed to the output layer. You see, the same is also passed back to itself. Whatever the state is in between, we are calling it as a memory loops. This is the in-between state. Whatever the output is generated, the same is coming back as a feedback to the same nodes, right? So this is recurring. The feedback loop has to be there, right? It's not compulsory that the feedback loop should come from the output only to its own. It can come, the output of this can be fed as input to this one. So there are different types of the recurrent neural network. This is the easiest recurrent neural network, which is vanilla recurrent neural network. There are improved and advanced version of the recurrent neural network. So see, we are calculating, this is a smaller version of this one. We have the input which we are considering as a xt, then we have a depth unit. So whatever the input I will pass, from that the output will be generated. So whatever output is there, I am calling as a ht, right? Now the same output is passed the another layer, here we are calling it as a memory nodes, here it is a day. So the same output will now act as an input for the next iteration, right? So that's why it is now acting as a ht-1 for the next t, right? So we are using the previous output as an input for the next generation, right? This is the equation which can be calculated, which can be derived from here. So sigma is nothing, it's just activation function. WHX is the weight between the hidden and the input, here, whatever is the input. This is the weight which is there from this to this, WHH. Then BH is again the bias, which is bias on the hidden there. This is weight between the Y and H. So whatever the weight is between the hidden and the output, same is mentioned. So based on that we are calculating. The only difference is that we have the recurrent. So we need to consider the output which is being generated right now as an input for the next time. Okay. Now the next one, a little bit improved version of the RNN. So what happens in the case of RNN is when we have too much of temporal dependency. For example, my today's result is not only dependent on the just previous result, it may be dependent on the previous maybe 1 week prior, like electricity load forecasting when I was saying. So in that case, it might be possible that I should be using another type of neural network which is called as an LSTM, that is long short-term memory. So what it says is, first you need to find out the dependency, whether it exists or not. If the dependency is high, then you should use it. So there is a problem in both RNN as well as in the case of the LSTM, which is called as a gradient vanishing problem and gradient exploding. There are two problems which occurs. So it says that whatever the gradient is nothing, I don't know in how detail you are aware, but when we are calculating the error output for every neural network, we do calculate the output, and that output should be used to update the weights, right? I'll give you just a small basic idea that how it works. Consider this is a simple neural network, right? And here we have calculated the output y, right? So let's say this is x1, x2, and I have the output of x1, x2, and based on that we have output, let's say yp, right? Now based on this input, I will calculate some output because there will be some weight assigned to it. Let's say this is W13, this is W3. I said that these two are randomly decided. It's not that we already know what should be the value. Because if you see the equation of this one, yp has to be W13x1 plus W23x2 plus of, let's say bias is also there, and volume is B3 plus B3. You see the total input which is coming on this node is the output, right? So I started with two random numbers of W13 and W23 within the range of -1 to 1, right? But we started with the random numbers. For any machine learning algorithm, it is mandatory to find out the best curve fitting equation. I hope everybody is aware of the curve fitting equation, right? So I need to find the best equation that should give us the best value of W13 and W23. If I get the best value of W1, both of these two, and as well as bias, for the testing, during the testing time, what I have to do is simply have to pass the value of x1 and x2. I'll get the new value, right? I can predict the value. If I know the equation, for example, if I like, let's say this equation I got 0.3 of x1 plus 0.2 of x2 plus of 5. Let's say I got to know that W13 is 0.3, W23 is 0.4, and P3 is 5. Right? This is the final equation which I have got. It means after training my model, I got to know that now if I provide the value, different value of x1 and x2, I can predict what should be the next output. Right? During the training, we get the curve fitting equation, the best curve fitting equation. Once the model is trained, we provide some random numbers or any test data to generate the output, right? So in this case, what I'm trying to say is, whatever the output we have got here, for the first time, whatever randomly it needs to be upgraded every time, because I said 0.2 and the other weight was 0.5. That was random. When I'll calculate the error at that time, I will get some different value, which is not an appropriate. It says that my weight should be updated. My weight should be updated is by, which is called as a delta rule actually. So these are updated, so that's why there is one term here in the LSTM, right? So whatever the error is the one used to propagate back and update my weights, let's say W12 and W13. Okay? So start with random. But when the LSTM is there are so many, if you see this diagram, you see there are so many number of connections. This is the one connection, one cell which is there, very similar to your artificial neural network. This is one neuron, and there are several number of neurons which will be connected. And there is a long dependency between the data, right? So what happens that whatever the error we are generating at the end, that error will be utilized to update the weight. But what happens when we go back in the direction or when we are updating the weight, at that time that value becomes very, very small, that error component becomes very, very small. So that's why we call it the gradient is vanishing, because we are losing the gradient. So that is a very big problem with the both RNN as well as the LST. Right?
Excuse me.
Yes.
How weights have changed?
How weights have changed?
Then how you say that particular value of weight is
So what happens when we create when we have those network, we have to start with the random weights. We need to assign. We need to assign these values randomly. First we are starting with the random. But when we say the model is training, what happens? The weight is, during the model training, the weights are the one who are updated.
How it is being updated?
So for that we have different method. One is the delta. In the case of a perceptron, we use the delta rule, which is called as, let's say I'm updating this one. So it says that W13 this is the new value, which will be W13 plus of alpha into, let's say this is x1, this is x2. So this is alpha into x1 into what is the error B. So let's say the error B what is E0. So the error which we are calculating, because I'll predict the value first, I'll first generate the output here because I have given my input. So if you remember just now I told you earlier, summation of Wij xi plus of y's Eg. That's the bias is here. So if I randomly started with this value and this value, and I know the inputs and I know the bias value, I can calculate the output. Everything is known here, right? I started with these two random numbers.
That means it is value, next value, that means being influenced by input also.
No.
Next one you are
Yes. Yeah. It is basically, if you see, every time it is actually mostly influenced by my error. If my error,
X1 is also there.
X1 is there, but the input has to be always there, right? So, input is always there, right? The only thing which is changing is my error, right? Alpha is my learning rate, it is always going to be fixed. Input is also fixed. The only thing which will change every time is error. If error becomes 0, if my input is 0, then there is no concept of updating the weight. You see, if input is 0, then why I am training the model? There is no purpose of it. For the particular input, I want to find what should be the best value of the weight, right? If input remains something, if input is 0, there is no purpose of updating
What's
this.
the alpha?
Alpha is the learning rate. At what pace or at what speed you want the weights to be updated.
This is constant or dynamic?
Yeah, mostly it is constant. Nowadays we have a question too, that is a step method and all are there. But most initially it has to be fixed between 0 to 1, any value. Okay. Now this error is the one which is very important. Maybe probably for the first time when I predicted the value, I got let's say 0.9. But actual value should be 1. Let's say the target is 1, but I got 0.9. So the error is 0.1. Based on that, my weight will be updated to some new value. Okay. And similarly, the bias will be also updated. So these are the basic concept which is there for perceptron. From there only the same other models which has come up in the CNN and all, they are all using it. So they say that okay, we can update the weights always by whatever the weight is there plus of alpha into input into N. This is always there. But this approach is called as the delta rule. And nowadays there are others like SGD, which is the stochastic gradient descent. Then we have RS-pop also. There is an Adam optimizer also. There are other but advanced version of this delta. This is gradient rule. Delta rule is nothing but a gradient descent approach. So they are used to update the weight. They are telling that which best algorithm you can use it so that you can update the weight. So finally what happens is that during this whole machine learning algorithm, the weights are the one which are every time adjusted. So if you see, if I am running the algorithm or the numerator for 100 times, my weight will be updated for 100 times. But when it will stop, when my error becomes 0, right? If there is no error, it means my model has learned properly. There is no difference between what is predicted and what is actually given, right? So I should stop at that point, right? So later on, let's assume that there is always some small error, and for the 100 iteration, I got that weight, and the weight has been updated. Now at the end, I will be having a question which would be somewhat similar to, like I said, W1 for let's say x1 plus W2, W12, x2 plus of let's say biases. Now I got the best values of W1 and W2 during the training. So let's assume it is 0.3 of x1 plus 0.5 of x2 plus of 0.9, let's say. This is what I got. Let's say after training I got the best values of weights and the biases. Biases are also updated in the same manner plus of alpha into n. Same is there. X we are explicitly not writing it, but because the input is basically 1 or minus 1. now you see, after training, if I got this equation, so during the testing, what we have to do is simply pass the value of x1 and x2, right? Because the data is, most of the time we are given with the data. So most of the time we are given with the data x1 and x2. And what we do is, the whole data is divided into 70-30 ratio. Most of you might be aware, right? 70% are used for the training, remaining 30% will be used for the testing. So those 30%, x1, x2 values which are there, one by one I will pass into this ratio, I will predict the value, right? Now based on that prediction, I will say whether my model is accurate or inaccurate, right? So this is how all the machine learning algorithms work. The equation is very, very similar for all of them, whether it is a support vector machine, it is a linear regression, or it is application learning. For all of them, we are going to have a similar type of coefficient equation. And during the learning, every time we are finding the best values of the coefficient. You see, W11 and W12 or the bias, what are they? They are coefficients only with respect to x1 and x2, and V1 is a constant, right? Very similar to the mathematical equation that we have for the simple line of equation, the y equals to mx plus c, right? So this is the architecture of the LSTM. This is for the one unit. You see there are several number of the gates here. So there are 3 gates. One is forget gate, input gate, and the candidate cell gate. So for all of them, we do calculate the values. Whatever the value comes up, based on that we directly calculate what is the final output. You see the final output is EV, which is coming with the edge. Along with this and this, they are used as input for the previous level, right? So you see how many number of the cells we are having. Based on that, we have written the timestamp, right? So if you are calculating for CV, we are using the CV minus 3. So it is up to the programmer to decide that how long we want to go back to predict the value, which will be how long we want to see, or how much dependency I want to show on my current output, whether it will be for the 7 days or maybe 24-hour data, depends on that. The next one is GRU. It is very similar to the LSTM, but it is not now dependent on the temporal dependency of the data. So it's very similar to the previous. We have the reset gate and the update gate, but in the previous, if you see, having forget gate, input gate. So they are very much similar. The only difference is now it is not used for the temporal dependency. The other is the transformer and the attention mechanism. Like it can be used for the different cases. For example, when we are having the multi-sensors, which are there in the autonomous driving system. For example, the data collected from the camera, from the LiDAR, or from the IMU, whatever the data is coming now, they all can be used together, and on that we can implement this transformer and attention. This is for the transformer and this is for the attention. This is from one of the paper. You can go through this one. They have used it specifically for the analysis of the genomic data. They have used. So they can use for the creation of the synthetic data too, if it is not available. Then this is about, like when we are talking about the electric vehicles. Let's say if I'm talking about the autonomous electric vehicle. In that case, we need to go with the object detection, right? So now the object detection comes into the mostly into the computer vision, right? So in that, there are different types of the models which has come up. So this is the timeline, or the evolution of how the object detection algorithm have been used so far till 2023. So even this YOLO VA, that's what I'm going to discuss. There is YOLO V9 also, which is available. So based on your data type, you can decide which type of the object detection algorithm is going to work for you. So that's YOLO. You only look once. It's a very single shot. You can. This is a single shot data. It looks at a particular image, then it detects a particular image in a very short span of time compared to the previous one. Like you can use the CNN for the object detection too. But this YOLO works better compared to the CNN because it takes a very small time. So the time complexity for this one is very less. So what it does is, it takes the image, then it creates the bounding box around the in the image, and it classifies, it creates the class in one particular task. Let's say whatever the image objects are there, for each of the image it will create a bounding box, right? And based on that bounding box, it will identify that what is that object. So it is a one-go shot, right? So how does it work? it's actually the advanced version of the CNN itself, and basically it is suitable when we are going to have images which is taken with a high frame per second, right? The number of the frames are very high, then it works very well. And when we have like large number of data, because the number of the frames are going to be high, so that's why they require GPUs and the benefits too. It can be used for the detection of the pedestrian because it is an object detection. So what are the objects which are coming in the front of the vehicle or behind the vehicle, so that no collision happens. So what are the vehicles, who are the pedestrians, there, what are the lines, are they following the lanes or not? There is side lanes, lanes which are coming in the side. If there is any collision which can occur, then it can give a warning also. So based on that, these detection can be done. So basically it's the image detection type of, right? Object detection or object detection.
Is it for video? Is it for video?
You can actually take it from video, apply for the video. From the video we are applying on the object actually. It's like it can be used for the drowsiness detection also. Like if you see if the driver is driving and then there is a drowsiness, so in 1 second or maybe within 2 seconds, how many number of the frames it is taking. So it is a video, but later on when processing is done, it is on every frame, not on the whole video together. So this is the architecture of YOLO V8, but YOLO V9 is also available. So there, it just started with a simple YOLO, but there different versions are there. So now, if you see, we have talked about these are all related to the deep learning models, right? The basic deep learning models. But along with the deep learning, there are other things also which help, right? For example, optimization techniques. Right? I have not written too much on the optimization, but there are optimization algorithms such as, you might have heard about genetic algorithm maybe, some of you maybe about Parkinson optimization algorithm. They are a little bit old, but still they are being combined with the other models because they have some specific features which lead to the very good research work also, right? So here we are talking about what type of optimization algorithm can be used to enhance the parameters, or you can say enhance the accuracy of the model. So just now I talked about this GD, gradient descent. SGD is stochastic gradient descent. Then mini batch is stochastic gradient descent. So these are the approach which are used to enhance that how I can update the weights, how the weights can be updated in a more appropriate manner, right? So these are the optimization techniques, right? Then there is the ADAM, which I said RMS prop is another optimization technique. So when you will be using this calculation in the network, you can change the type of the optimizer also that you can do. So when we are using all these, there is a very high probability of getting a good results. So the convergence is very fast for both the problem, for finding SOC and SOH of the battery. Then whatever the model we are creating with the help of these optimization technique, they are going to be stable. So you all must be aware that how we say that the model is stable when we are getting the similar result every time. I am executing the same program for 100 times, but if I am getting the same result almost approximately 95% every time, I will say my model is stable, right? But if one time I am getting 91%, next time I am getting 97%, then my model is not stable, right? So when we are creating a model, any artificial model or any machine learning model, it should be stable as well as it should be accurate. So there are other approach also like regularization method. So L1 and L2 regularization approach are there. They are basically used in one of the example I can give you is support vector machine, which is used for the multi-class classification. They are using, right? Even this regularization approach can be used for again stopping of when we are having an overfitting problem. So in the machine learning, we talked about the two types of the problem. One is underfitting, another is overfitting problem. So sometimes we are having very sufficient amount of the data, but my model has learned too much of that data that when the new test data is coming, it is not able to classify it properly because it has learned that thing very properly. The new data it is not able to identify and classify, right? It's like when we are teaching a student with this particular topic only in too detail, and when we are asking something new related to that topic itself, they are not able to answer, right? So that is the problem of the overfitting. Another is underfitting, that we have a limited amount of data, on that we have trained our model, right? Now we are asking for something which it is not aware of. So again it is not going to respond well, right? So having a sufficient and a good data is very important in the case of the implementation of any machine learning algorithm. when we want to apply for the, find out the robustness of the battery degradation model, then also we can apply this degradation. For overfitting problems in the EV sensor anomaly detection, like if you have to find out whether the sensor is working very well or not, if there is a fault or not, then also we can apply this models. There are other normalization approach, like we talked about the Z-score and I said Min-Max normalization is there. We can go out with the other also, like dropout method, batch norm. These are all directly available in the Python. You want, you can apply it for your application. So I will explain this one. In the case of the dropout, you are deciding that how many number of the weight connections should be considered. Even the CNN also, there are several number of the connections. You want 10% of the weight connection should not be considered. You can ignore that 10, right? So that way the time complexity will be reduced. So it is also defined in the CNN. So there are different case studies are there actually where you can apply this AI/ML or the deep learning model. So for learning the smart vehicles, in that case we can use the CNN. I said that when for the object detection which is there in the lane, or the people who are coming, or people who are crossing the lane, or people who are moving, the pedestrian who are moving, for all those things you can go to the object detection. For that you can use CNN. An improved version of the CNN is RCNN, which is faster than the simple CNN, or recurring CNN, sorry, it is a recurring CNN. Then the YOLO we have also discussed, faster RCNN is there. Transformer based we have seen, transformer attention. Then they can be used for the detection of drowsiness and distraction of the driver, right? They can be also used for automation of the driving by sensing what are the data which is coming from the different sensors and from the different cameras on the images. Right? So these are the different areas where the AI can be used for forward collision warning, for automatic emergency braking, blind spot detection, all those things are there. Where you can see. These are not the only areas. You might find that application of AI in your area also, which you are working. I'm sure that in 95% cases, there is a very high probability that you can use AI. Even if you are taking two numbers, from your side, you are deciding that these two numbers should be considered for my, let's say, any system. So that two numbers which you are deciding from your side, itself can be replaced by the logic system. Itself can be replaced by the feature selection algorithm. So try to find out something from the AI, or you can say from the background of the machine learning, which can help you out, and I can ensure that, in the most of the cases, it is going to improve your result. Because what you are deciding, these two numbers are good. If AI can decide or machine learning can decide, it will be much better. I'm saying for the application purpose. Right? Don't say that AI is always going to be good, right? But in most of the cases, it can help you out when you are randomly deciding on any numbers. Right? So for this, there are different algorithms which can be used. So for the sensor fusion algorithm, you can use the Kalman filtering. This is mostly used. Sensor measuring algorithm is also used. So we are taking the data which is coming from the camera, radar and the radar. Now you have to decide which model you want to use. Okay? For the object detection which is there, we have already discussed that which models can be used, right, and how it can be used. And what are the target objects which could be there, like what are the obstacles, if there are cones, potholes, and if there is a road line market, all these things. There are other previous also which are discussed. You can consider all those objects in your application, and then if you want, maybe there is a very high probability of being able to switch to it. There are similarly other deep learning models which can be used for the battery management system, like finding whether the battery is working well or not, if there is a faulty, or what is the state of SOC and SOH estimation time, which can be used by LSTM. You can use the combination of CNN and LSTM. You can have bi-directional LSTM is there. There is another LSTM which is called as the stacked LSTM, which you can implement in yours. The transformer based, which I showed earlier. So based on your application, you can find which model is going to be appropriate for you. This is where for the charging infrastructure, if you want to use the deep learning, so it can be used for the station level load forecasting, finding that at this particular station, what is the peak time and what is the peak load which is required. And the anomaly detection in the chargers, whether the charger is working well or not. like what is the queue time. By using the RNN you can use it, then you can find it out. You can use the DRL, that is dynamic reinforcement learning, to find out the dynamic pricing optimization. You see, every time we have a fixed amount of the price. If the competition is very high in the street, the lane is very if there are so many number of the cars in the queue, at that time that is the peak time, so you can increase the amount or you can decrease the amount of the price of the EV charging. Right? So this is one of the paper I've given this as a source. So here they are using this AI-based explainable AI system in order to detect the driver anomaly, if there is any drowsiness or why the driver is driving or not. Right? So if you see, there are they have used three types of the deep learning model. The one is ResNet, then DenseNet, then the Inception V3, which is the part of the Google. So what they did is, whatever the input they have given to all the three models. They predicted their own result. All the data was given to all the three models, they have given the three results. Now later on what they are doing is they are combining all the three results. They are giving it to the XGBoost classifier, classifying that which one is giving the best result, that will be considered for the final prediction. Right? So this is the hybrid model they are using. Then there is another paper which is discussing about what is the charging behavior of the electric vehicle by using two approach. One is fuzzy, another one is C-mean clustering. So I have talked about just unsupervised learning approach, saying the clustering word. So there are different types of clustering, C-mean, K-mean, and there is hierarchical clustering. So it is combined with the fuzzy counting. So you see this diagram is there from the paper. So what they are doing is they are collecting the data from the EVs. After that, whatever the data having, arrival time, parking time, charging time. So this is two-dimensional data, the one is one-dimensional data. So whatever the data comes up, based on this one, what they are doing is they are generating this fuzzy C-mean clustering. They are doing this clustering, right? So that's why a simple clustering is there, but they will combine with the fuzzy. So that's why they have called it the fuzzy C-mean clustering. Now the fuzzy set is there. Later on, they have passed with the neural network. So this is simple neural network. Now from the neural network, they are classifying into the categories. From there itself, now whatever they have got from here, they are obtaining the list of those individuals who should be given as a priority, those users who should be given as a priority while charging. Right? So they are classifying the charging behavior of the users based on this algorithm, that is fuzzy and the C. Right? So if you see nowadays what is happening, that most of the algorithms, they are trying to combine, they are trying to create a hybrid model. One of the model may be performing well, but when they are combined with the other two, the problem which is there with one of them can be negated by the another algorithm. There is a probability. So that's why most of the research paper, if you focus or see, they are talking more about the hybrid models. Right? So this is all about this presentation. If you have any queries, then we can have a question.
Madam, how AI or ML is used for fault detection?
If we can collect the data, let's say it's from the charges. So without data, the machine learning cannot work. Without data, how it will work? How will it predict? Anomaly detection is prediction, whether we're saying there is a fault in the charger or not. So you need to see when it goes, we need to collect the data, then from the charger, that what are the things, let's say the flow of the electricity. I'm not very into the electrical, but just what are the parameters can be decided in order to decide that the exact amount of the electricity flow is there, or the charger which is there, it is also, if it is getting charged, so how much time it is taking to charge the charger itself, right? So all those parameters which could be there, that should be considered to collect the data. When there is no flow from the charger, if the EV is not getting charged, it is faulty, right? So, but we need to see that where the degradation is happening, which one is that parameter, in that the change is being kept occurring for maybe 1 month or 2 months, and it was not noticeable. Maybe for the first time we didn't got to know, but maybe for the year, if I collect such type of data, from that pattern we can go to, we can get to know that if this is a thing happening, maybe degradation in this particular parameter is the one which is deciding that my charger is failing, otherwise they are not able to charge it, right? So we need to have have a sufficient. I'm not very aware of what parameters can be there, data parameters should be considered, but there will be always a change in one of them, maybe two of them, which is the deciding factor for this anomaly detection in the charger or in the charging station.
We use Kalman filtering to estimate state of charge or state of breakup of battery.
It can
How
be.
is this different?
So Kalman filtering, I haven't implemented the Kalman filtering, but I have seen the papers. I can suggest that the Kalman filtering, which was proposed very long back, but if it can be replaced with the other, like, it is just we classify
The
the
question is
model.
also, can we replace or can we add on with Kalman filtering?
Kalman filtering, sorry, that hybrid model I don't
Without
know.
ignoring Kalman.
But sir, if you can explain me what input parameters, what type of parameters you are giving into that model. The same can be even given to the other models, like you can start with the ANN, you can start with the support vector machine, they are also used for prediction. So I cannot ensure whether the Kalman is always going to give or this one, but at least for the testing purpose we can, or for the different child, you can think of, because this ANN are now artificial based, they are always getting enhanced. But the Kalman filtering is still the same, and which is much older compared to the ANN with respect to the research.
In one of the slides I have seen multi-sensor fusion.
Sir?
Multi-sensor fusion.
There are several sensors which are there. When combined together, so together we are calling it a multi-sensor. Then we are combining all the results which are coming from several sensors.
360 degrees.
Whatever the different sensors we are putting on the Dept, from all those sensors, whatever the data is coming, right? Or even there are simple sensors which can work for the different things. So same sensors can collect the different information. Like pressure, the same can collect for the temperature. So such sensors, if I am collecting the data from them, sometimes the integration of the data or the data which is being collected may not be accurate. So there is a problem with working on such type of data. If there is an inconsistency in the data or the mistaken data. Because the sensor is the one data, right? If it is sensing one data correctly, but another data which is being collected by the same sensor is not good, right? Or not good, or not fine. In that case, my model is not going to work, right? Model only works on the basis of the data which we are providing. If I provide the synthetic data, it will give the result based on the synthetic data. If I am providing some different or a vague data, then